Dear students, welcome to my video class. Today I talk about one of the important concept like charge transfer spectra under spectral and magnetic properties. In spectral and magnetic properties or the electronic spectra of transition metal complexes normally due to DD transition or the colored complexes or the color transitions are due to DD transitions. But some cases the transition metal complexes show an intense color in solution but possesses no DD transition. Means without DD transition, some of the inorganic compounds are colored bands. How? Because of in transition metal complexes, a change in electron distribution between the metal and ligand gives rise to the color bands, and that bands called charge transfer bands. It shows under UV as well as visible light. It depends on the change of the type of transitions. There are two types of electronic spectra. One is the DD spectra or DD transition spectra, and another one is charge transfer spectra. First of all, the DD spectra or the DD transition means the electron which moves from lower d energy level to the higher d energy level. Means based on the Orgel diagram or based on the Tanabe-Sugano diagram, we can easily interpret the DD transition spectra. Means in these are spin allowed transitions. Means either Laporte or Tanabe-Sugano diagram or Orgel diagram mainly based on the spin allowed transition. That's why these are due to the DD transitions. And another one is the charge transfer spectra. The charge transfer spectra means the spectra originate from the redistribution of electron charge density within the molecules. Means the charge transfer band arises from the movement of electrons between orbitals that are predominantly in a ligand character and that are in metal character. Means the transfer of electron from ligand to the metal or electron moves from metal to ligand. That is called as charge transfer spectra. Means the electron transition between metal to ligand or ligand to ligand or other types. These transitions are identified by their high intensity and sensitivity of their energy to solvent polarity. Means the charge transfer spectra generally observed in UV region because of its energy gap should be maximum. And these transitions are more intense than DD transition. Means the DD transition or the charge transfer spectra. In here the charge transfer spectra, these are redox transition. Redox transition means both oxidation as well as reduction. Either ligand can reduced, metal will be oxidized, or reverse cases. That's why it is an due to the or these are redox transitions and mostly occur in UV region because of the charge transfer energy is greater than DD transition. The DD transitions are colored bands. The color bands are easily observed under visible region. But as energy gap increases between lower to higher, it moves on to the UV region from UV visible to UV region. That's why in here charge transfer spectra, the energy gap is maximum, hence most of the cases which is observed under UV region. And most of the thing is, most important concept is they are Laporte and spin allowed transition. Because in a DD transition, it's only spin allowed. Some cases the Laporte allowed, but they are very weak intensive. But in case of charge transfer spectra, they are Laporte as well as spin allowed transition. And almost all the complexes, it shows the CT or the charge transfer spectra. In here, it can be classified into, or the charge transfer spectra classified into, there are four types. One is ligand to metal charge transfer, metal to ligand charge transfer, metal to metal ligand or metal to metal charge transfer, ligand to ligand charge transfer. Means LMCT, MLCT, MMCT. The metal to metal charge transfer is also nothing but intervalence charge transfer, and ligand to ligand charge transfer also nothing but interligand charge transfer. So these four classification are very important, not only the exam point of view but also in CSIR, NET and SET examination. That's why it's very important concept. The first one is the ligand to metal charge transfer transition. The ligand possesses either the sigma, sigma star, phi, phi star and non-bonding molecular orbitals. If the ligand molecular orbitals are full, charge transfer may occur from ligand molecular to the empty or partially filled metal d orbital. Because of ligand to metal charge transfer means the electron which moves from ligand orbital to the metal orbital. Then what are the criteria or what are the important points which involved in the LMCT, ligand to metal charge transfer? You can observe in the figure, these are the ligand orbital and that is the metal orbitals. Consider in an octahedral geometry, the octahedral geometry, in case of the example for the D6 system, there are 6 electrons in the degenerated orbitals, and based on the ligand strength overlap to metal ion, in here the metal electrons which are in the lower T2G energy level and the fully filled ligands which moves from lower to the higher EG energy level. Means the electron which moves from filled ligand or phi donor ligands to the empty or partially filled metal d orbitals. In here the electron which moves from ligand orbital to the higher EG energy orbital, the transition metal complexes. So what are the conditions required in LMCT? In here the first point is the transfer of electron from filled ligand to the vacant d orbital. Means the ligands are fully filled orbitals and metals are either the vacant orbital or the partially filled orbitals. Means one of the degeneracy should be either empty. In that cases, the electron moves from ligand to the metal. And generally the ligands are phi donor ligands. Consider example like halides, oxides, sulfides, selenides, N3 minus, RO minus. These are example for the phi donor ligands. And metal orbital should have high energy vacant orbital. Means the metal is electron acceptor and ligand is electron donor. And metal must have high oxidation state, means +2 +3 +4 Mn +4 +2 +5, which will be more favorable to the LMCT possibilities. And internal oxidation of ligand and internal reduction of metal takes place because of it's a redox transition, means either the ligand should be oxidized, metal should be reduced. In reverse cases, metal should be oxidized, ligand should be reduced in some cases. Next, the what are the factors affecting the change of LMCT? So LMCT means the electron moves from lower ligand orbital to the higher metal orbital. Due to this LMCT, either ligand metal charge transfer increases or decreases in different types of complexes. So that will be explaining under the factors affecting change of LMCT. So the first one is the LMCT energy increased from 3D level to the 5D. Means in periodic table, as moves in the transition metal transition metal ions from top to bottom, it moves from 3D, 4D, 5D. Means vanadium, ruthenium in these cases, or 3D, 4D, 5D cases, the energy should be increased. Or from the figure we can observe that is the lower ligand orbital, that is 3D, 4D, 5D transitions, means it moves to the top to bottom. 3D is the topmost metal d orbitals, next 4D, next 5D. As the energy gap from lower ligand to the 3D orbitals, in the 3D the energy gap should be smaller. As it moves to the 4D, 5D, its energy gap should be increases. And next is moving from left to right in the periodic table, like the 3D transition metal ions like vanadium, uh, chromium, manganese, iron, cobalt. In these cases, as move on from the left to right, the LMCT should be decreases. So you can observe in effective nuclear charge increases, size of the shell decreases. Means the size of the atom decreases due to the effective nuclear charge. Okay, as the size of the atom metal transition decreases, LMCT energy decreases. It having the same ligand can be explained. Consider in the case of in observing in here, suppose hexa aqua vanadium complexes or chromium hexa aqua chromium complexes or hexa aqua manganese complexes. In these cases, aqua is the ligand, same ligand. It moves from lower ligand to the higher metal and lower ligand to the chromium or vanadium. In here, its energy gap should be decreases from left to right. In the vanadium cases, its energy gap should be increases, and in chromium as it decreases. At the manganese, it should be very small compared to the chromium and vanadium. Means it moves to the left to right of the periodic table. The LMCT value should be decreases. Means it increases the color. As LMCT increases, it moves to the UV region. LMCT decreases means it moves to the visible region. Next, the same metal atom having different oxidation state, like in the case of ruthenium 2 plus, ruthenium 4 plus, as the ligand should be same, but its oxidation state of the ruthenium should be varied. In here, its LMCT should be increases from lower oxidation state to the higher oxidation state. Means LMCT decreases on increasing of oxidation state of the metal. And the fourth point is, suppose the metal should be same but ligand should be changes and LMCT is also changes. How? In case of halides like ClBr, as its atomic number or the size of the ligand increases from ClBr, its LMCT should be decreases. That's why in case of HgCl2, mercury chloride white color, bromide yellow color, and iodide is red color. We can observe in this figure. LMCT should be increases, means it moves on to the UV region. LMCT decreases, it moves on to the visible region. And next one is metal to ligand charge transfer. Is the one of the type of charge transfer spectra. Means the electron which moves from lower metal orbital to the higher ligand orbitals. So in here the transfer of electron from molecular orbital metal to the ligand orbital. The metal must have less oxidation state. Means these metal ions are fully filled orbitals and ligands having vacant phi acceptor. Means the ligands are vacant orbital or phi acceptor, metal is phi donor. Example of phi acceptor ligands is carbonyl, cyano, NO, pyridine, phenyl ring, thionato, imines, aromatic ligands. These are the example for the phi acceptor ligands. And ligand should having high vacant energy and metal having the lower energy. So that is uh, the ligand 5 star orbital having the vacant site and the metal orbitals having the fully filled orbitals or the rich electronic state. The electron which moves from lower metal orbital to the higher ligand orbital or the 5 star orbitals forms the metal to ligand bond formation. These are observed under the molecular orbital of octahedral geometry. In here one is phi acceptor or phi donor ligands. So it depends on either the formation of metal to ligand bond for covalence bond formation or ligand to metal covalent bond formation. Based on that, its charge transition takes place. In the electron rich metal shows colored because of its Eg to the phi orbitals. These energy gap should be very small and they are colored complexes. Next is metal to metal charge transfer. Is also nothing but intervalence charge transfer spectra. So it's defined as the excitation and subsequent transfer of electron from low oxidation state cation, means Mn plus 2, to neighboring cation of higher oxidation state, means neighboring metal ions in the bridged complexes. These are observed in the bridged complexes. In these cases, electron which moves from metal to metal, one of the lower oxidation state of the metal to the higher oxidation state of the metal causes the metal to metal charge transfer. Some compounds possesses metal ions in two different oxidation states. One is plus 2, another one is plus 3. These compounds charge transfer transition may occur when the electron moves from one metal ion to the other. Consider in the case of KFe3, Fe2, FeCN6. In here, that is the Persian blue color. In the first cases, Fe3 to Fe3 to Fe2 transition causes the Persian blue color, and Fe2 to Fe3 in the second cases that are Turnbull's blue color, because of one of the metal ions will be reduced and another one will be oxidized. In the first cases, the reduction takes place. Fe3 electron moves from Fe3 to Fe2, and in the second cases, Fe2 to Fe3 means oxidation takes place, or oxidizing agent which changes the color of the complexes. Means in the both the cases the transfer of electron from metal to metal only, but they are having the different oxidation numbers. Based on the lower to higher or higher to lower, it will oxidation or reduction takes place and forms the metal to metal charge transfer. And last one is ligand to ligand charge transfer. In a ligand to ligand means transfer of electron from one of the ligand to the neighboring ligand orbital. In here, the ligand electron which moves from lower ligand orbital to the higher ligand orbitals, means both oxidizing and reducing agents are present. Means one ligand acts as a phi donor and another one ligand acts as a phi acceptor. In here, the phi donor ligands donates an one electron to the phi acceptor ligands. In case of BeCO3X complexes, should L reduced state to the metal to L oxidized state, means reduced ligand to the oxidized ligands, means transfer of electron from ligand to metal to again ligand, and in here carbonyl acts as a phi acceptor and halide acts as a phi donor. In the second cases, TL bipyridine I2 is yellow colored because of I2 acts as a phi donor and bipyridine acts as a phi acceptor. That is also called as inter-ligand charge transfer. So these are observed in the special cases, ligand to ligand or inter-ligand charge transfer, that is observed in the special cases that gives the colored complexes due to the uh, charge transfer spectra. In here, there is no DD transition, but also shows the colored complexes or the colored bands due to charge transfer spectra. So these are very important concept under the charge transfer spectra. So thank you for watching my video.